In section 8.6, we take what we now know about momentum and center of mass and really begin to analyze the motion of a system of particles. Our objectives here are to connect center of mass to momentum and force to predict complex motion in systems of particles. This is where the center of mass idea becomes useful and significant. If we take the derivative of the position of the center of mass with respect to time, we find an equation for the velocity of the center of mass, where again v sub I equals the velocity of just any particle that is a piece of the system. So remember, our equation for the position of the center of mass was 1 over m multiplied by the summation of these m's times their position. Now if we're taking a derivative of that position with respect to time, that position now becomes a dr dt instead of just an r or an x, and really now we're looking at a velocity. So what we find here is that if we rearrange this a little bit, this big capital M can be moved over to the other side, so we've got a total mass times the velocity of the center of mass equaling the summation of all the little tiny bits of mass times their velocities, basically the summation of all the little tiny bits of momentum. What we're seeing here is that this is an expression proving that the total momentum of a system is equal to the total mass of the system multiplied by the velocity of the center of mass. So the momentum of a system is really just like the momentum of a single particle with the mass capital M moving at the velocity of the center of mass, which means that treating objects or systems as a single particle truly is a valid simplification model. If we now differentiate the equation with respect to time again, we find an equation for the acceleration of the center of mass. So again, we're going to take another derivative of what we have here. We still have that 1 over m, and rather than writing it as a v, we're going to look at the derivative of v with respect to time, and we get a dv dt. dv dt is really just acceleration. So again, rearranging and bringing the capital or total mass over to this side, we find that the total mass times the acceleration of the center of mass is really equal to the sum of these MAs, or the sum of the total forces acting on the object. Again, Fi is just the force acting on any particle within that system. So if we were to add up all of the forces acting on that object or on that system, it might be internal forces and it might be external forces, but we could add them all up. And when we do, what's going to happen to all those internal forces? Well, according to Newton's third law, they're all going to be equal and opposite, so they'll all just cancel out. And really, what we're saying is that the total mass times acceleration of the center of mass is going to be equal to the total sum of all the net forces acting on the object, where those net forces can be boiled down to only external forces acting on those objects, since the internal forces will cancel. Since we now have seen that the mass times the velocity of the center of mass is equal to the total momentum of the system, we can make a few substitutions here in terms of these derivatives and find that if we were to sum up all of the external forces acting on the system, which is going to be equal to mass times the acceleration of the center of mass, where acceleration again can be rewritten as dv dt, what we're finding is that we're really looking at this as a change in the momentum of the system. That the total momentum of the system will only change when there is some sort of total sum of these external forces acting on the system. And the total external forces will be equal to the mass times the acceleration of the center of mass, or that time rate of change of the momentum of the system. Again, this really means that all motion can be looked at in terms of the center of mass. Notice in the diagram here how the wrench, as it moves across the surface, it's rotating and the motion looks very complex. But the motion of the center of mass is not complex. It's moving along a straight line with a velocity that's decreasing due to friction between the wrench and the table. And you see that the white dots representing the center of mass follow a very predictable pattern. They're moving along a straight line, and you see that those dots become closer and closer together as this object is slowing down or decelerating due to that frictional force that is acting from the outside. Now, if the net force is through the center of mass of the system, then this object would be accelerated without any rotation. It's like pushing on the wrench right through its center of mass. And if you were to push right at that center of mass, the wrench will just simply slide across the table. If you instead push somewhere that is not at the center of mass and the external forces are applied somewhere other than the center of mass, then the wrench will begin to rotate in the pattern like you see in the diagram, but the center of mass will still follow the very same pattern and that very same predictable path. So if the net force is 0, that means that 0 net force is going to result in 0 change in the momentum, or basically the momentum is going to be constant. So with 0 net force, momentum is going to be a constant value. That means that the linear momentum of a system of particles in an isolated environment is going to be conserved. So let's say that we have a projectile that's fired up into the air, and when it's fired up in the air, it suddenly explodes. So maybe this is a firecracker or a firework. And when it gets here, the whole thing explodes into this big mess, and fragments kind of go flying every which way. The question is, what happens to the center of mass of the system? Or what could be said about the motion of the center of mass of the system after the explosion? Now, the center of mass of the system was in the middle of our firework, or whatever this is here, and it was following a very, very predictable path. Now, once the thing explodes, what I want you to recognize based on what we just said is that this center of mass is still going to follow the same predictable path. Although various fragments might go shooting off in various directions, the center of mass of all of those fragments will continue to follow the exact same predictable parabola that the initial center of mass was following. And the reason for that is because this explosion is due to an internal force. Internal forces do not have the ability to change the center of mass motion, or that velocity and its direction. So we could turn this into then maybe a simpler problem. Let's say that we maybe have a 1 kilogram object. And let's say that this 1 kilogram object is just flying straight up at maybe 10 meters per second. And as it's flying straight up, maybe this thing explodes. So after it has exploded, we have one fragment that maybe is, let's say that it's 75% of the original mass. So 75% of this, upon exploding, ends up moving maybe off to the left. So 0.75 kilograms is now flying off here at some new speed. And the question is, where's the rest of the stuff going to be going, and how fast is it going to be moving? Now, the remaining 0.25 kilograms of this object is also going to continue to move. So we have this piece moving at some VF over here, and then there's another piece of this system that is also going to be moving. There's 25% of it, or 0.25 kilograms, moving off in some other direction. What I want you to recognize here is that we can take these explosion problems and we can basically say that the total center of mass, motion, and momentum is not going to change. So if the initial momentum of this system was simply the 1 kilogram moving at 10 meters per second in a y direction, the final momentum of this system has to be the same. So this 0.25 kilogram piece is going to have some component in the y direction so that the total momentum of the system still stays the same. So if we take the 0.25 kilograms multiplied by then the sine of this angle theta and its velocity, that would be basically the y component of this fragment's momentum. Now in the x direction, the initial momentum, so this was the y direction, in the x direction, this thing's initial momentum was 0. None of it was in the y direction. So that means that the total final momentum in the x direction also has to be 0. So this piece over here, having its component of the momentum, would be the 0.25 kilograms multiplied by the cosine of our angle, and that final velocity of, piece number 2, maybe we could call this, and this is piece number 1 here. That piece of the momentum is really going to have to completely counterbalance the momentum of the 0.75 kilogram piece that is moving off at its final velocity. So problems might give you various components or pieces to this, but ultimately the idea is if you know that the center of mass of this system still has to follow that predictable path and that the center of mass still has to maintain its momentum, then even when this blows up into several fragments, that total momentum of the system still has to stay the same. I still need a total of 1 times 10 or 10 kilogram meters per second in terms of its momentum in the y direction at the end, and I still need a total momentum of 0 in the x direction at the end. So even though many pieces might go flying in several different directions, we know that the total initial momentum of this system has to remain unchanged. We'll try more of these problems together in class when you guys come back.